complex SYK and black holes this afternoon, sorry. But first I want to wish you a Happy New Year. It's a very special year. I discovered, I didn't figure this out, but it's the smallest numbers that can be written as the sum of the squares of 3 primes in 6 different ways. Okay, see if you can prove that. Okay. Well, okay, so someone asked me after my first lecture is why, which quantum models are supposed to be dual to gravity? Why am I looking at SYK? What's so special about it? So from my point of view, what's special about it is an example of what I would call quantum matter without quasi-particles. And so perhaps it's interesting to pause and just discuss what do I mean by that. So the way I defined it was, suppose you could compute all the many-body eigenstates of the quantum system, some large quantum system. So it has an exponentially large number of many-body eigenstates, and let's just focus on the lowest energy levels. Can you take, which are still exponentially large, can you express them in terms of some single particle parameters, like the single particle energy, the single particle interaction, and so on? And if you can, well, then you have quasi-particles. And if you can't, well, then this is an example of a system of quantum matter without quasi-particles. So, but the trouble with this definition is defining something for what it's not, and that's not always usually a good thing. So let's try to make a more positive definition, and that will connect it with things I'm going to talk about today. So a more positive definition would be, let's say, no poles in Green's function. So if you're told that if you have poles in a Green's function, that's an indication of a quasi-particle. That's true. So if you find a pole in the Green's function, you've got a quasi-particle. But there could be a system where you look very hard, you never find a pole, but yet there could be quasi-particles because you haven't looked hard enough. You haven't looked at the right degree of freedom, the right coordinates. And there are examples of this. There are theories we thought were strongly coupled CFTs, which just turned out to be in a dual formulation of free field theory. So if you hadn't known that duality, you wouldn't know. Also, if you didn't have translational symmetry, then also this becomes complicated. There could be quasi-particles, but there are no poles because the eigenstates have a complicated wave function. They're not plane waves, so you don't know how to look for them. So this is also not very useful.
What do you mean by Green's function of what?
Well, that's the question. So if I give you a system in the lab, this is impossible to do, even numerically or experimentally. We never have this information. So we need a better criterion. So you could do a scattering experiments and look for poles, look for particles coming out. And if you see a particle coming out, good, you're all set. But if you don't, you still don't know. That's the point, that there could still be something, you just haven't looked hard enough. You haven't done the right sort of experiment with the right sort of variables to see your particles. Okay.
Are you happy with poles that are off the real axis also?
No, I want to be on the real axis.
Really on the real axis?
Yes. Well, at very low energies. Oh, sorry. So they can be a little bit off the real axis, but they should approach the real axis as energy goes to 0. That's what happens in Fermi liquid theory.
So no poles means also that you don't have the bound states?
Well, no. So so at low energies, the bound state would then become your particle. That would be your quasi-particle. So if you look for the Green's function of the bound state, you'd see a pole, so you're fine.
So the interaction is not binding. That's
Well,
what
no, I'm not saying that at all. I'm saying you look for whatever the particle is. I mean, it may be that the particle of the theory, the ultimate particle is a bound state of the UV theory. So if you look at the Green's function of the UV field, you won't see a pole. But if you look at the Green's function of the bound state, you'll see a pole. So that's fine. That's a system with
Confining theories are examples of theories where no poles.
No, there's a pole for a baryon. That's a system. Any gap theory has quasi-particles.
So the only theory, CFTs are examples.
Yeah, so we'll come to examples, but let me first finally state the best criterion that I know of, which is you have to look at dynamical properties, lifetimes, thermalizations, and the modern era out-of-time autocorrelation functions. That's really the way to tell. So 3, you could look for thermalization time. That's the way I thought about it a long time ago. That is, you kick it a little bit, and then you watch how long it takes to thermalize. Now, this is quite easy to define in a zero-dimensional system. When you go to finite dimension, there are subtleties with conservation of energy, leading to long time tails. And the improved way to do this is the OTOC, which for a while people thought had cured those problems. So the better way to look at it. But in fact, they also have similar issues. So we don't have a completely precise way to do it. But for each system on a case-by-case basis, there's a way to define a suitable time. And then what you have to look for is whether this time, whatever, let me just call it tau thermal, is long or not. So if this is long, then we have quasiparticles. And if it's short, then there are no quasiparticles. And what do I mean by this? Well, if you have quasiparticles, when you create an excitation, it just breaks up into particles. And what that means is those particles can be identified and they move along independently of each other, i.e. they don't thermalize. But eventually they have to find each other and collide. And as Boltzmann showed, even the gas in this room does thermalize in some time, and that time is basically the mean collision time between the molecules. And that's similarly true in a quantum system. So there's some collision time that has to be long. And then that's an indication that if your thermalization time is long, that you probably do have some quasiparticle excitations. So notice I'm not making any reference to what they are. I'm just looking at how long it takes to thermalize. And similarly with the out-of-time autocorrelation function, you're looking for some chaos. And I'm sure Douglas will say a lot more about that, so I won't go into it. But this again raises the question, long or short compared to what? What is there, so that another question that becomes, is there a shortest possible time? Suppose you have a system with without quasiparticles, how rapidly can it thermalize? And so from a variety of indications, and now there's a lot of other considerations, what we believe there is a shortest possible time, and this tau thermalization is greater than or equal to some constant. In the case of OTOC, you can fix the constant even, h bar over kVt. So the time is just temperature itself. And to be more precise, for the case of thermalization, I'm referring to a temperature of the final state. So as the system approaches some final state, which is thermal, then there's some exponential decay towards the final state. And we want to know how long it reaches the final state. And if it reaches very rapidly, this becomes an equality. So if this is equal, then we would claim that there are no quasiparticles. So this is just a conjecture, but it's supported by lots of evidence. Yeah. So at times longer than tau, this is local. So I should say.
Classical hydrodynamics, so h bar is 0. So I would have said it's usually classical hydrodynamics. We say is locally in equilibrium, but then it has.
Yeah. So that's okay. So if I suppose I have a little box here and I kick it here, then in this region there will be some local thermalization. I'm talking about that. Now what will happen? That energy will start to diffuse. That's described by hydrodynamics. That can take very long. It can depend on system size and lots of other things. I'm not talking about that. Hydrodynamics is a very general theory of conserved flows. I mean, another interesting thing to realize is that the theory of hydrodynamics was written down the Navier-Stokes equation before we knew there were molecules. So it doesn't depend on quasiparticles. It's a very general thing about fluids without even knowing their particles. Yeah. Of course they have. That's why they thermalize. Well, then the thermalization time will be infinity. So in a Fermi liquid, so let's give some examples. So in a Fermi liquid, I don't want to erase this. Okay, I'm going to erase my magic formula. So this is step 3 here. So in a Fermi liquid, you find that the tau thermalization is the collision time between particles, which in fact I worked out last time. for that simple random matrix model, and it's basically kBt squared, sorry, the other way around, some Fermi energy over kBt squared, and then probably an h bar over here. So that's a much longer time than 1 h bar over kBt. Okay, so that's much longer, and it certainly satisfies the bound. Now, for the SYK model, I haven't computed it, but it's a complicated job to actually compute thermalization, and Douglas will show you, I'm sure, how you compute the OTOC. But we have computed numerically, or one way you can see what it's going to be is just by looking at the Green's function. So when I showed you the form of the Green's function, the fermions, so G of SYK, and it had this form, which is pi t over sine pi t to the 1/2, and at pi t tau. Okay, this was an imaginary time, but we notice here, and this is in units when h bar and kb is 1, that there's a very natural time scale here that over which this has some dissipated behavior, and that's tau of 1 over temperature. And it doesn't involve the coupling constant at all. So that's another indication that, in fact, the SYK model has no quasi-particles because it thermalizes. It's not, this doesn't show it, doesn't prove it, but it's a strong indication that it's in the same class. Okay, now to return to David's question, what about conformal field theories? So many conformal field theories, of course, also have correlation of this type, but they still do have quasi-particles. That's because they, in fact, don't thermalize, and in fact, all the minimal models of this type, in two dimensions, they have some dual representation where they're nearly free. Maybe large central charge CFTs in 2 dimensions don't thermalize, do thermalize and don't have quasi-particles, but we don't really know how to solve them except through holographic duals, or even what they are. In 3 dimensions, of course, so historically, I would say the first system that was found and studied and understood, not in this language, but we can now look back and see that's what they discovered, was the 3D Ising model, or the 2 + 1 dimensional Ising model, which is described by the Wilson-Fisher fixed point. So that's a strongly coupled conformal field theory, and is the first real example of a system without quasi-particles. Okay, but another very famous example of a system which has exactly this property is, of course, a black hole. So if you take a black hole, and in fact, if you look at the LIGO data, you can even look for this. You have these 2 black holes colliding, and all kinds of complicated things happen. But eventually, the black holes become a perfect sphere. And just before they become a perfect sphere, they're in some elliptical shape, and they oscillate a bit, and they come down to rest. So you can ask, how long does it take for that last relaxation of the black hole to perfect sphere? And that has been worked out a long time ago from Einstein's equations. And if you combine Einstein's equation with Hawking's subsequent work on what the temperature of a black hole is, that time is h bar over kt. So this is the quasi-normal mode time. I should say that here somewhere. So for a black hole, there's some quasi-normal mode ring down time, and that's also scales in this way, where this is the Hawking temperature. So that's, in fact, I would say, one powerful way of understanding, why is it that there may be a gravitational dual and a black hole representation of a system without quasi-particles, because they share this rapid thermalization. And of course, the new language is in terms of chaos, which is even more precise. Yeah.
This statement is not clear what its content, because there is only one scale in the problem.
No, that's not true. That's not true.
Modes are proportional.
Okay.
Modes are proportional for a Schwarzian black hole,
Right.
Or is it important to
It doesn't matter what black hole you have.
For a Schwarzian black hole, you have the Schwarzian size.
Right.
And then the ring down time or the ring down frequency
Okay.
is proportional to the
Right.
Schwarzian size.
Okay.
And the temperature, of course, is also h bar over the Schwarzian.
Yeah. All right. Fine. I mean, maybe it's dimensional analysis that.
Dimension is constant, so it will not be.
Okay, but you can look at many black holes that have more than one dimensional parameter. This will still be true. I believe that's correct, but I'm not an expert on black holes.
That doesn't mean it's trivial.
Yeah. Okay. I mean, yes. So
Why should it have a temperature at all, right?
Relies on a very key property of black
Yeah,
holes.
Yes.
Exactly. If there's a temperature, it has to be this, but why a temperature at all?
It's tautological, maybe it's not trivial.
okay. All right. Let me move on. Okay, please. I am not going to win with the black hole expert. Are you a black hole expert? Okay. What else am I going to say? Yeah. All right. So what I want to talk about today is something that Igor has mentioned off and on, which is that the SYK model and charged black hole in anti-de Sitter space, in fact, generic charged black holes and spherically symmetric black holes in anti-de Sitter space share the same low energy theory. And that theory is the Schwarzian theory that's been mentioned several times, and I'm sure Douglas will say a lot more about it. I'll indicate how it's derived from the SYK model and also how it can be derived just from the Einstein-Maxwell theory of a charged black hole. Okay. Now, some of you might wonder, why is it that this wasn't done earlier? I mean, the theory of black holes, charged black holes, has been known for a very long time, and many people have been quantizing gravity in all sorts of ways. So why wasn't what we now believe to be the universal low energy theory of these models known before? Well, I would say Almeri and Polchinski almost got it. They came very close, but at the end of the paper, they seemed rather confused as to where this was all going and what their results meant. But soon after, with the work of Kitaev and Maldacena and Stanford, I think the whole picture clarified tremendously. And the reason it clarified, I think, philosophically, something I like to believe, is that you cannot underestimate the importance of having a UV complete theory. So what SYK gave you was a UV complete theory that's completely finite. And it told you, when you quantize gravity, how you got to do it. Which infinity should you ignore? Which mode should you focus on? What's an artifact of cutoffs and what's not? It's not obvious at all. But if you have a UV complete theory in front of you, you know what to do. And so that's worked out. All right. Now, this is not to imply that if I actually had a physical charged black hole in our universe in some anti-de Sitter space, its theory is the SYK model. That's not true. Maybe, but certainly don't know that. There may be some other UV complete theory. But what I'm going to claim is independent of the UV complete theory, there's certain universal features of the low energy quantum mechanics that's described by a single theory across all charged black holes, which are spherically symmetric. The other, what was it? Oh, also, there's a lot of work from string theory on charged black holes. Those are invariably have supersymmetry, n equals to supersymmetry. Those have a different theory. They have a very different behavior at low energies, which can also be understood now using a supersymmetric SYK model, which shares many features with the supersymmetric theories. Okay. All right, so with that preamble, let me wander where I know very little, which is Einstein-Maxwell theory and gravity. So what we're just going to construct, and I just remind you some features of the solution of Einstein-Maxwell theory. So we take, let's work in 4 space-time dimension. This is the Ricci curvature. Is a negative cosmological constant. L is the parameter determining the curvature of space. This is the electromagnetic field, and this is some gauge coupling constant. So you look for a solution where the metric is spherically symmetric in the angular coordinates, and it's stationary, so it only depends on the coordinate r, and t is time, and this is the angular coordinates. So if you plug this in here, look at the equations of motion, which I have actually worked out, believe it or not, with the help of a Mathematica program. You find it's solved. We just take a VFR of this type. And you also allow for an electric field, which is sourced here in this gauge by a time component of vector potential. So there's various parameters here, theta, m, and mu, and so on. We'll fix them in a minute, and r naught. So what are all these parameters? So first of all, this metric has the feature as r goes to infinity, only this term appears. and you can put this over here and here, and that turns out to be anti-ADS4. So it's asymptotically ADS4 as r goes to infinity, and the boundary of ADS4 is a big large sphere, S2, and that's the omega, and that's the radius as r goes to infinity, and time, in imaginary time anyway, that's the time circle. So it's S2 cross S1 as that's the boundary of the theory. You also have to add here some counter terms. There's not just the so-called Gibbon-Hawking counter term, but there's additional terms that you also have to include, which are all totally known to give you a finite answer. All right, so then with this particular metric, we choose the R0 is the point where V of R0 equals 0. Black hole horizon is V of R0 equals 0. So that defines the root of that potential, defines the horizon of the black hole. And we also choose the 0 of the chemical potential, the vector potential, so that that vanishes on the black hole horizon. Okay, so there's a black hole here. This radius is R0. And at this point, A tau is 0. And V of R is also 0. So these are just, well, this is required, and this is just a choice. You can always shift A tau by a constant. But it's a good choice to make because as A tau goes to infinity, that turns out in the ADS-CFT framework. So if you go to infinity, A tau R goes to infinity. Well, that turns out to be the chemical potential. This is the same chemical potential I had in the complex SYK model yesterday. Okay, so then it turns out this is a solution. You get a 2-parameter family of solutions. So of course I assume all the coupling constants are fixed in the action. You just solve the equations. You get a 2-parameter family, and they're completely, and it's convenient to take them to be the chemical potential and the temperature. So you give me a mu and T, all these other things are fixed. R naught, theta, m, they're fully determined. That's not actually true in flat asymptotic space because the mass of the black hole and the charge are independent, but not in anti-de Sitter space. Okay. So the mu determines the charge of the black hole. So as you increase mu, you put more and more charge, and the black holes become bigger and bigger and bigger. And so there's 2 scales here. One is the radius of the black hole, and the other is the curvature of the anti-de Sitter space, which is given by L. And I'll take them to have any ratio you want. Doesn't matter. Okay? So that's the summary of everything I know about general relativity. Any questions? Or I used to know a lot more in graduate school. I don't remember a thing. Yes? Because of the anti-de Sitter space boundary condition. It just turns out that the equation doesn't work unless M and Q are fixed. Yes? Well, so there's the Gibbons-Hawking term, for example. So when you compute the action, the action is infinite because you're really computing infinite space. So it turns out, however, you want to identify the action, including the counter terms of the grand potential. So mu t is basically going to be in the Euclidean signature anyway. So this is the S Euclidean over T over temperature, give you the grand potential, should be just this. So you evaluate, for this solution, you evaluate this expression, and that gives you the grand potential. So
you should emphasize the counter terms are only at the asymptotic boundary.
Right. So they're just
boundary terms.
They just depend on this structure. Once you know this structure, they're completely fixed. Well, they depend on L. That's it. The counter terms do depend on L. But they don't depend on mu or the T. Anyway, so you put all this in there, you solve it, and you get an expression, and my mathematical file has a complete expression of omega as a function of mu and T. Okay? All right, so now I can turn into a condensed matter theorist because this is just some thermodynamic system. I know it's free energy as a function of chemical potential and temperature, and compute all sorts of things. So what are the things you can compute? You can compute the entropy, which is minus d omega dt. And when you do it, you magically found, yes? mu. So mu is the chemical potential, which determines the charge. So this is a charged black hole. So there's some charge here. There's a charge in the center of the black hole, Q, and there's an electric field going out to infinity. Yes. Okay. And out at infinity, I assume there's some other surface which neutralizes it, but you don't have to worry about it. It's at infinity. So it's just like a point charge far enough away. Okay. And the value of Q is fixed by mu. If you put mu equals 0, then Q becomes 0, and this becomes the Schwarzschild's ADS Schwarzschild solution. Now, there's an important reason I'm treating mu non-zero, because the horizon of this black hole is quite different from ADS Schwarzschild black hole. That's where ADS2 will come out. That's why I need the mu crucially. Yeah.
Are you saying this is the same thermodynamic system, or are you saying this is actually an ADS of the charge?
So certainly, I could take the SYK model and I can compute omega of mu and T of the SYK model. I gave you the expression for that. And this is not the same function for sure. It's a completely different function. So the equation of state, the free energy, are totally different function. This omega and mu and 2 depends on, and everything here. If I add r to the squared term, other terms, it will change. So it's a highly non-universal thing. So now what I want to do is identify certain universal features. And that's where I'm going. There are certain features that are universal, which will be shared by the SYK model and this model. And I'll begin by identifying features which are shared even at this level, even at the level of classical gravity. There are some things that are common. But it goes beyond that, beyond classical gravity. Semi-classical gravity also shares features with the SYK model. All right, so you can compute the entropy, and this turns out magically to equal the area of this, which is 4 pi r naught squared, a over 4g, which is Hawking's formula. And all of this comes right out. And again, it's important to keep all these quantum terms for that to work out. In fact, on the flight over, I was awake the whole flight because this wasn't working out, but it worked out.
It's wrong to call them counterterms. They're really boundaries.
Okay, sure.
Terms in the
Yes.
Classical gravity.
Yeah.
They're just
There's the first term, the Gibbons-Hawking term, depends on extrinsic curvature, but the other depend on the internal curvature of the boundary. Those are more appropriate counterterms.
Is it required to give the correct renormalized mass and?
Yes, they're absolutely required, but they're out at infinity. They won't be that important for us, I believe, because we're eventually going to zoom in to the horizon. Okay. Also, the other thing you can compute is the charge of the black hole, which is minus d omega d mu. So that will give you the charge. And then you can compute S as a function of Q and so on. So first of all, and you can compute the compressibility, which is dq d mu. So the first common thing you find between such black holes and SYK model, well, there's two. I'm running out of space. I'll do it over here so I can erase this. Or so first of all, S as t goes to 0 for a sufficiently large mu is non-zero. It's S0. And you can also compute the first term, and I'll call that gamma t. So this gamma will play an important role in what I'm going to talk about. It will be related to the coefficient of the Schwarzian. Now, I haven't computed this for the SYK model, but believe me, if you do it, you do get the same term. And so now if I want to match the SYK model with the black hole, I'm going to match these quantities. I'm going to match S naught, I'm going to match gamma. Okay. Then you find, of course, that the charge Q as t goes to 0 is not 0, it has some charge. And the compressibility, which is dq d mu at t equals 0, is also not equal to 0. So these are all properties shared by the SYK model. Okay. All right, so now next what I want to do is just zoom in to R, because in the near horizon region. Okay, so take t goes to 0, take t goes to 0, and R goes to R0. In fact, let me just take t equals 0, but you can know, I don't have the answer written out for general t. But anyway, take R goes to R0, and you define your radial coordinate. R is R0 minus, okay. And all the explicit expressions are actually in the notes. Yeah. So R is R0 minus, I'll call it R2 squared over zeta. So these are all constants you can fix. And basically you're trading R for zeta. So you have a new coordinate, zeta. Let me use a different color chalk. So there's a coordinate zeta which goes to infinity right at the horizon of the black hole. Zeta, and it's infinity here and goes to 0 out there. Okay. So, sorry. What did I do? Yes, I want a plus. Thank you. Right. So now I take this limit, take the 0 temperature limit, and ask what happens to ds squared. So in this limit, you find exactly at t equals 0. There's also you find the following metric. This becomes d zeta squared minus dt squared over zeta squared with an R2 squared here, I believe. And there's also an R0 squared d omega 2 squared. Okay. So this is a very special metric. So the one thing you notice with this metric, first of all, is that this function v of r, as it approaches R0, has a double 0 at the horizon, at 0 temperature. So that's what you call an extremal black hole. If you had mu equals 0 and did a Schwarzschild black hole, you would not find this double 0. You wouldn't have the zeta squared. You'd just be a zeta. So that's a different Rindler type geometry. This is anti-de Sitter space. So the charge is absolutely crucial for that. So this geometry is what's called ADS2. And in this case, this is just an S2. So there's a factorization of the geometry into ADS2 cross S2 right near the horizon of the black hole. So what seems to have happened is that all the transverse directions have decoupled from the radial excitations. So this is a four-dimensional theory that we started with, and now at very low energies, and in fact at temperatures, I suppose I can erase all of this. So at temperatures much smaller than 1 over R0, we can ignore all angular modes. And the theory effectively becomes gravity in 1 plus 1d. And the two dimensions are zeta and time. So this part you can just ignore and just focus on the radial part. All right. So that's the special feature of ADS2 black holes. And there's been, in fact, a lot of papers written trying to quantize and understand the dynamics of black holes. In fact, about 8 years ago, when I was working on the SYK model again, looking at holography, I read a lot of those papers, and I couldn't make head or tail of them. I had a hunch these were related somehow, but I couldn't make it work. Looking back, I think those papers were also confused, not just me. Yes.
Suppose that you add to this four-dimensional also a complex scalar field. That's also has a solution, and the holography corresponds to some.
Yeah. So
is there any deformation of the SYK that will correspond?
So if you just add a scalar field, this factor won't change. It'll renormalize some of these couplings, but it won't change this. Now, if you had a scalar field with couplings, you need some renormalization of dilaton factors here with coupling that scale with the strength of the scalar field, like phi squared, f squared terms. Then you can get different solutions. They are so-called hyperscaling, violating, and Lipschitz solutions. I don't want those. Just talking about the ordinary. You can add scalar field, nothing will change. Generic scalar fields. This will still be true. Yeah.
Nor do the angular modes correspond to throwing out supersymmetry?
There's no supersymmetry here. So this black hole is not supersymmetric, even in this limit. There are other black holes that are supersymmetric. They actually have very different properties. Yeah. Well, this is the cosmological constant. It's negative. Yes, you need it. You need it to get the ADS4 behavior at infinity.
Yeah, but to get the ADS2, you don't, right?
Well, there's other ways of getting ADS2 in neutral black holes. Yeah, okay.
The rising Nernst string in asymptotically flat space is also ADS2.
Yeah, that will also be variable.
Yeah, that's also ADS2.
I know, but then, okay, it's probable. Okay, good point.
Yeah.
It's possible what I'm going to say also applies in that case in asymptotic flat space, but I don't quite know how to make it work. I'm trying to be a little more cautious. I'm making a lot of bold statements. I'm not going that far. Because I think there's some question on how you actually quantize something in asymptotically flat space. You know, all these quanta terms are really crucial, and nobody knows how to do that. All right. Oh, so first of all, the metric becomes this. Then let me just yeah. The other thing that happens is let's ask the gauge field. So what happens to the gauge field? So the gauge field, as r approaches r0, that becomes, where is this? Okay. Yeah, so A tau becomes E over zeta, basically. That's it. So this is actually a dimensionless number because A tau is dimension of inverse length, and this is 1 over length. So just a pure number. And this script E, in some units, depending on R2 and other things, is a measure of this electric field. So it's the electric field right at the surface of the horizon. The horizon, as zeta goes to infinity, and there A tau goes to 0, as that was a boundary condition. But the way it goes to 0 defines the number E. Okay, this is a dimensionless measure of the electric field at the surface of the horizon. All right, so now it turns out there's another relationship between the quantities I've defined here and this E. So this is just purely a property of gravity. It turns out that this ds naught by dq at fixed temperature, which is going to 0, is equal to 2 pi e. So this was a relation which was actually first proven this way by Ashok Sen. So it's a matter of looking at Einstein's equation near an ADS2 horizon and looking at it carefully in very general conditions, you find this is true. And this is now again another thing which I essentially proved this relationship yesterday, starting from the SYK model. Exactly the same relation. Now you might say, well, how do I define E there? Maybe I just chose a clever definition that this worked out. How do I match the values of E? Here E is the electric field, there E was something else. Now you may remember there E was an asymmetry in the fermion-Green's function. So you can do a similar thing here. Let's compute a fermion-Green's function in this ADS2 space. So so you have this ADS2 metric now. All right, so this is zeta going to infinity. Black hole horizon is way over there. ds squared is dt squared plus d zeta squared over zeta squared. And then you put a fermion, Dirac fermion here, and you compute by the rules of the ADS2 correspondence the Green's function of psi. So this was actually first done by Faulkner et al. Faulkner, Hong Liu, John McGreevy, and Iqbal. So you compute G, and of course there's also an electric field. This is a charged fermion with unit, so this is a charged fermion, charged. So it also feels the vector potential, which is A tau is E over zeta. And so you compute it, and if you look up their G in their paper, it has exactly the form that I wrote down yesterday. It's 1 over tau to some alpha for tau greater than 0, and 1 over tau to the alpha times e to the minus 2 pi e for tau less than 0. Exactly the form I wrote down for the SYK model. In fact, that's why I wrote it down this way, because I was looking ahead and matching to this. So this is, if you wish, the definition of E. If you take this definition, Einstein's equations, i.e. Ashok-Sen, show us it's the same as this definition. What about alpha? Well, this alpha can be anything at all in this theory. It depends on the mass, the bulk mass of psi. You can choose it to be 1/2 if you want, but you can be anything else. It's not fixed in the pure gravity theory. In the SYK model, certain things are fixed in a universal way by the UV behavior. For example, the value of S0 here is nothing special. It can be anything you want. But in the SYK model, it's a very specific value. So the things are much more constrained, but the structure is basically the same. Yes? How is what? I'm sorry, this is imaginary time. That's real time. Okay. Any other questions? That was easy. Okay. All right. So I think that's all I have. Oh, but let me also actually say a few more words about the reduction to 2D. So from 4D to 2D, you can make it a little more formal. You can start with the Einstein-Maxwell theory there, and take very generally, take a 2D take a metric of this form. So I'm going to take a metric much more general than the one I wrote down earlier, but I'm going to ignore the angular fluctuations. So I'm going to write the metric as G alpha beta of dx alpha dx beta. Here alpha beta equals x and t. So there's two-dimensional gravity. And then I have the angular coordinates, which are d omega 2 squared as before. But the coefficient I'm going to call phi of x and t. Sorry, r. Phi of r and t. And I'm also going to put a factor of 1 over square root of phi over here. And g also depends on r and t. So this is really the most general metric, four-dimensional metric consistent with spherical symmetry. And phi can be any function of r and t, g can be any function of r and t. So you take this and plug it in here and evaluate the whole mess, something I did this morning. And what comes out is the following. You get, in fact, what's called the Jakob tidal bond gravity. I guess what? 2 pi, 8 pi, 16 pi g, 4 pi g here, I guess. No, 4g. D2x, square root of, let me call this h to prevent confusion with that, g, square root of minus h. And you get phi of the 2D curvature plus some v of phi minus z of phi over L squared F squared. So this is a purely 2D gravity theory, which is equivalent to this 4D gravity theory in the spherically symmetric approximation. And it involves not just pure gravity, but a scalar field. And what is that scalar field? The scalar field represents the radius of the black hole, which can fluctuate in principle. So this, without the v of phi in this term, with a constant v of phi, this is what's called the Jakob tidal bond theory. Now, what Almeri and Polchinski showed was that actually it didn't depend very much on v of phi. You could take almost any v of phi near a saddle point, provided there was a radius to horizon. The properties are basically the same. And in the charged black hole case, you just get one extra electromagnetic field mode. All right. So this theory is somehow related to 2D gravity, and I'm sure Douglas will say more about this theory and its quantum fluctuations, which I'll briefly refer to. Okay. All right. So what I've presented so far is just large n limit in the SYK model, exactly at n equals infinity, and classical gravity, supplemented with Hawking's formula for the entropy, that's where h bar comes in, and temperature. So if you take all of those results, what we see then, there's a very interesting match in this formula here. So this tells you, how you throw some charges into the black hole will grow, the entropy will grow because of the area will grow. Tells you how much it grows per charge. It depends on the electric field on the horizon. That's all. Yes?
So when Almeida and Polchinski explored this model and
Yeah.
they added quantum matter, in the entropy they found a term which went like log T.
Yeah, I don't know that.
Is there any analog of that in?
Okay, so I must confess I don't know this, but my guess would be that's not right. That they were, I think, if one is done at that point, they hadn't understood the details of the entropy. In fact, they were in fact, precisely on entropy, there were many statements that I know are not correct. We know are not correct today, so I would suspect it's not right. Yeah.
Where's the electric field in strange metal?
What? Sorry?
Where's the electric field coming from in the strange metal?
I'm not talking about strange metals. Okay, so right, so this is just a number E. Okay, I'm only calling it an electric field in the context of the gravity theory. So there, I computed the Green's function. I had this form, and E was just a parameterization of the asymmetry between positive and negative time. You can also view that as a parameterization of the particle-hole asymmetry. So if you compute the Green's function in some system and you remove a particle, it has some Green's function, or if you add a particle, in general that's a different Green's function. For example, if I take the SYK model and suppose it's mostly full, I put 3/4 n fermions in a system with n sites. Well, it's going to be easier to remove a particle than to add a particle. They're going to have the amplitude for adding a particle be much larger than the amplitude for removing a other way around, because there's so many particles to begin with. It's only at half filling where E is 0. Okay, so that's just a particle-hole asymmetry. That's all. In fact, I used that in a crucial way. That was how we first computed the value of S0 for SYK model. All right, so fluctuations. So let's go to fluctuations. So the fluctuations rely on a key property of this metric, the ADS2 metric. It has a very large symmetry, or an isometry really, which let me just remind you what it is. Here, so it's more manifest in the imaginary time. So we go to imaginary time when you're really talking about hyperbolic space, not ADS2. So in imaginary time, this is the metric. So what I invite you to check, and this is certainly something I've checked, if you define a new tau prime and a new zeta prime, both real numbers, by the following transformation, A tau plus I zeta plus B over C tau plus I zeta plus D, where AD minus BC equals 1, then this metric has exactly the same form. It's T tau prime squared plus D zeta prime squared over zeta. So this set of transformations with A, B, C, D are real numbers is what's called SL2R. So there's a very large SL2R symmetry of the ADS2 metric, and that's going to play, of course, a crucial role in the analysis of the fluctuations. There's another global symmetry here, which is a gauge symmetry in the bulk for the charge case. That's the U1 gauge symmetry, which becomes a global symmetry on the SYK model. And that will also play a role. So both these facts are very similar to the color tensor model that Igor talked about. Of course, there's a difference there. The symmetries there, the global symmetries are much, much bigger. Here, just U1. But I think they play a similar role. All right, so where is this SL2R symmetry in the SYK model? So let me just describe that. Probably many of you have seen that. How many of you want to see that? Yeah, okay.
You saw it already.
Sorry? Well, I didn't actually discuss it. Okay.
But it's also not a symmetry.
Sorry. Okay. So how would you say it? What do you want to say it?
It's not a symmetry.
It's a gauge. It's a gauge invariance or something like that.
No, there's there's an isometry of the metric,
Yeah.
not a symmetry of the solution. It's not a symmetry of phi.
Yeah. Okay. It's a symmetry of the action in low energies. Yeah. Okay. So, all right. Maybe I should discuss it. Okay. Let me quickly discuss it. So, I'll discuss it at the level of the saddle point equation and not the action. Probably Douglas will say more about the action. So the saddle point equation, remember I showed you where G of omega is I omega plus sigma minus mu, all of omega, and sigma of tau is G squared of tau, G of minus tau. Okay, so the key is to take these equations and rewrite them in a much more suggestive way, focusing on low energies. So remember I showed you at very low energy this omega didn't matter because the sigma of omega was larger than omega. The mu also didn't matter because it cancelled with sigma of 0. So that also didn't matter. So it's only G sigma, and it's also actually sign minus 1. So this equation is just G sigma equals -1 in frequency space, but if we want to now write it in a double time notation, I want to write it as G of tau 1, tau 2, sigma of tau 2, tau 3, integral of tau 2 is minus delta of tau 1 minus tau 3. And this equation is also very simple, but I'm going to write it as a function of, I imagine it's useful to imagine for a while that the functions are not actually, the Green's function is not actually a function of time differences, but more generally it's a double time Green's function. So this would be minus G squared of tau 1, tau 2, and G of tau 2, tau 1. So this is the low energy equations, and these do have a huge set of symmetries. In fact, they're incredibly huge and tells you there's an infinite number of possible solutions, but most of those solutions are meaningless, not the solution we're looking for, because those solutions depend on two times. We're only interested in solutions that are function of time differences, and also have the right asymptotic behavior at large frequencies to fall off as 1 over omega, and that pretty much fixes the unique solution. But anyway, temporarily just thinking about these saddle point equations as two-time variables, and really the reason you want to do that is you actually set up the path integral of the disordered system, it naturally comes expressed in terms of two-time Green's function, bilocal Green's functions. This was something we had studied in great detail in the old days in the 90s, and when we were studying fluctuations. It's only the saddle point that depends on time differences. The fluctuation involve integrals over the bilocal Green's function, and that's why it's useful to consider them. Also, it turns out that the symmetries act much more naturally when you write them in this two-time argument. All right, so what are the symmetries? Well, there's two sets of symmetries. One is a time reparameterization. So, and this is also, as we'll see, kind of similar to gravity. And this theory certainly is invariant under time reparameterizations. The action for gravity, 2D gravity, is invariant under time reparameterization. The time of this SYK model will turn out to be the time of this gravity somewhere far from the black hole horizon in some asymptotic region. Okay, as is usual in ADS-CFT type mappings. All right, so you could write tau equals f of sigma, so you introduce a new time sigma, and then you write g of tau 1, tau 2 is f prime of sigma 1, f prime of sigma 2 to the minus 1/4 times g of sigma 1 over g of sigma 2 times g tilde of sigma 1, sigma 2, and then sigma of tau 1, tau 2 is the same thing, the same f prime here to the power minus 3/4, and then g of sigma 1, sigma 2, and sigma tilde of sigma 1, sigma 2. Okay, and also g of sigma 1 will later on take to be some e to the I phi of sigma. Okay. All right, so you can I invite you to plug this in here and verify that the equations for g tilde and sigma tilde are exactly the same form as these equations, with tau replaced by sigma. All the f's completely cancel out. So there's a time reprioritization symmetry, and this little g is like a global U1 symmetry. So this is an emergent symmetry. Even the U1 is emergent because it's a gauge symmetry. The SYK model as written down only had a global U1 symmetry, but this is a gauge symmetry. So there's emergent time reprioritization and emergent gauge symmetry. And then that's kind of like in gravity, the bulk has reparameterization of space-time, and boundary global symmetries become bulk gauge symmetries, and that's kind of what's happening here. All right, so that's great. So it seems like if you find one set of solution of this equation, you can just have a machine to generate an infinite number. But as I said earlier, most of those solutions are totally meaningless because they don't depend upon time differences. You notice that this factor here doesn't depend on sigma 1 minus sigma 2. So even if this depended on sigma 1 minus sigma 2, this won't depend on tau 1 minus tau 2. So these symmetries are important for the fluctuations, but they're not a symmetry then of the ground state, of the actual saddle point. So then you can ask, so there's some saddle point solution. Okay, so the saddle point solution is g of tau 1 minus tau 2. Tau 1, tau 2 scales is 1 over tau 1 minus tau 2 to the 1/2. So now you can ask the following question. So if here I have a machine, if you give me a g, well, you can write the inverse of this. If you give me a g, I can compute a g tilde. So I gave you a g, and I ask you to compute the g tilde. And I require that g tilde of sigma 1, sigma 2 be exactly the same. That is, it actually be an invariance of the ground state. So for a general f of sigma, this will not be true. And you ask, what is the largest possible set of f of sigmas? And this was shown by Kitaev to be exactly the symmetry I just discussed for radius 2, c sigma plus d. Okay, yeah. Yeah, so you've broken diffeomorphism down to SL2R. And the Schwarzian you can view as some kind of nonlinear sigma model when breaking SL2R down to, breaking diffeomorphism down to U1. Okay. All right. Similarly, this global symmetry here is no longer true. This gauge symmetry, U1 gauge symmetry is no longer gauge symmetry. It's broken by the ground state to global symmetry. All right. So that's one analysis of symmetries, and at this point it should be very suggestive that all of these symmetries completely match everything we learned from the black hole, have exactly the same structure. And it's those symmetries then, and the way they're broken, that ends up defining the nature of the fluctuations. Okay? So maybe I'll just go ahead then and just write down what the final form of the action is. Because I don't know, I'm not quite sure what Douglas was planning to cover, but he's certainly a better person to explain it since he's the one who was involved in first figuring this out. So from this, we can now, yes, half an hour left. Okay. Any other questions so far? Phi, sorry, this phi? Yeah, so this only works, so we require this, and we also require phi of sigma to be a constant. It cannot be dependent on time. So the U1 there seems to be an emergent U1 gauge symmetry, but at very low energies, but it's broken by the saddle point. And this helps up, so there's a broken symmetry, and that tells us the kind of Goldstone modes that you're going to look for. We're going to look for the Goldstone modes. Now, for U1, that's very straightforward. It is broken, and therefore you know how to do it. For the SL2R, there's a subtlety in the sense that the symmetry is only SL2R, but there are terms here that we threw out which do break the time reparameterizations. And so you do have to, so in fact, the coefficient of certain terms of the action depends on the UV structure through this I omega. Okay. And all of this, all of these subtleties on what's UV and what's not, I think only becomes clear when you have an explicit UV complete model to deal with. And part of the reason I think Fulchinsky and Al-Mahiri didn't get all the way. All right, so what is the final result? Okay, so let me kind of just sketch the basic idea. So we are going to evaluate the partition function, which is trace e to the minus beta h SYK. We're going to explicitly write down the partition function here. The very first equation I wrote down with the C daggers, I will ego wrote it down. You average over the Gij, you do lots of Hubbard-Stronovich decouplings, and this you can write as a path integral of G of tau 1, tau 2, G of sigma of tau 1, tau 2, exponential of minus n, some action I of G and sigma. So this is some functional. So this part can be done exactly with no approximation. This is true, and there's a factor of n out front and nothing nowhere else. So that's really the utility of this. The n dependence becomes totally clear. So all the gymnastics ego was going through with the colors, we don't have to do any of that. N dependence is very straightforward. Yes.
The saddle point is after averaging.
Okay, so what we do here, we have to do what's called a quenched average, but we're doing an annealed average. So you have to really introduce replicas and do it carefully. And in fact, that's what we spent 5 years studying in the 90s. We did it with replicas, believe me. And there are models, other variants of the SYK model, where that's very important, and you get spin glass solutions. But for this particular model, none of it matters. The solution is completely replica diagonal, and therefore I'm just ignoring it. And this is closely related to the question of self-averaging. We know this is. Yeah, we didn't know that at that time. It seems to be much more self-averaging than anybody expected. I expected. Yeah.
Well, he said it was a statement that was exact, right?
Oh, thank you. Right. If you go to time. Right. So again, this is something Douglas will talk about. So if you look at Green's functions or various correlation functions up to times of order n, there's no problem. Times of order n squared, you have to go to times of order e to the n, and then you start seeing sample-to-sample fluctuations, which don't self-average. Okay. But all right. So now you look at the saddle. So this is the path integral you have to evaluate, and this is way too complicated. Although we can write it down explicitly. And so now the idea is that you here's some very complicated G sigma space, and here's your saddle point. You found some unique saddle point solution, sigma s and gs, and that's in fact those saddle points there. You can do all this finite temperature. I haven't written that down. And now you have to look at fluctuations and integrate over everything. Well, that's way too complicated. So you're going to pick, there's a very complex space. You're going to pick a valley, which is not exactly flat, but nearly flat, which dominates. So there's some very special direction. And what is that special direction? About the saddle point, we're going to say that G is the transform, is this transform of G. So let me do it right here. I'll just replace this by the saddle point function. So I know these functions. So these are functions of two variables, sigma 1 and sigma 2. So I have two functions of two variables, two bilocal functions, and I have to do the path integral over all of them. I'm not going to do that. I'm going to replace that very large space by a very special direction. In that special direction, this function of 2 times is actually parameterized by two functions of 1 time, which is of course f of sigma and g of sigma, or phi. Okay? So along this direction, if I deform g and sigma along these symmetries, and the reason you want to do that is because the low energy theory, the action is invariant. The high energy theory, it's not. So you might think that the high energy effects will be very small, and so along these directions, the action will be very small. Yes, okay? So then you can rewrite this path integral as a path integral d of f of sigma, phi of sigma, times some action, some I of f and phi. Okay? With an n out front, of course, still. So this is an approximation. So this is the only first place we've made an approximation, other than the e to the minus n effects with averaging over disorder. Okay, which I think Douglas will say something about. I don't know how he's going to get through all of that stuff in 4 lectures. But anyway, okay. So now where we are in this whole game is that we know this action. So we can derive it by various methods using symmetries, and in fact you can derive this action starting both from the black hole theory I mentioned or starting from the SYK model. In the black hole theory you have to do some complicated stuff starting from the JT gravity and so on, and from the SYK model you have to basically look at the structure of the perturbation theory and some of these ladder diagrams that Igor had mentioned. Anyway, but all of that hard work is really only required to fix the coupling constants. You can pretty much know the general structure of this just from thinking about the symmetries a bit more. All right? So what is this I? Okay, so this is the I that I'm going to write down. So I turns out to be, so these are functions of single times. There's some action I, and it's the following. So it turns out at finite temperature, it has the following form, nk over 2, and time goes from 0 to 1 over temperature, d tau. Well, so first you have this d tau phi, and I'll leave a little space here, whole squared. Okay, so if this was just 0, then it's just phi squared. So that's due to the U1 symmetry. That was U1 gauge symmetry was broken to global. And you can see very generally it has to just depend on the time derivative of it. So this is a very simple theory. The way you think about this is what's called a rotor. It's just a rotor. Phi is a particle. So phi of tau is equal to phi of tau plus 1 over temperature. It's periodic. Is phi of tau plus 2 pi n. So I have to put that condition over here. Phi equals to phi plus 2 pi n. So you're summing over particle moving in a circle. And that gives you a spectrum of discrete energy levels. What are those energy levels? Well, those energy levels are precisely the cost for adding an extra charge. So you have the SYK model, a little dot sitting there. You add in an extra charge, its energy goes up or down. And that cost for adding extra charges is this grad phi squared. So in fact, if this was my entire theory, this path integral is dual to the Hamiltonian, then d phi of e to the minus nk over 2 d tau phi squared. This is easy to evaluate. That turns out to be sum over p e to the minus p squared over 2 nk t. Okay, so this is just the Hamiltonian here is p squared over 2 nk t. So this is the energy levels of a particle moving in a circle with mass m. M is 2nk. It's a very heavy particle. I'm going to tell you what k is. It is the k that was the k in the slides before. So this k, well, anyway, so this is just a bunch of energy levels. There's one here, and then there's two here. So this p equals 0, p equals 1, plus minus 1, and so on. This is, sort of like very much the formula of like q squared over 2c. It's like a capacitor. This is the capacitance. This is the charge. This is the energy of a capacitor or a quantum dot or something. And what this k is, the capacitance, or in this language, is the compressibility. How much energy to add per particle to raise it. So dn d mu, or, well, so the chemical, this term will be like a chemical potential. Anyway, so this k is basically dq d mu. So it's exactly equal to this. It is the compressibility. So if I know the compressibility of the black hole or the SYK model, I know this coupling constant here. Yeah, this is d phi of tau with those boundary conditions. You have to sum over all the instantons. Sorry?
The action.
Well, of course, yes. Thank you. This is quantum mechanics 101, particle on a circle, done the most complicated way possible. Okay, so it's just like what we call the Coulomb blockade energy, and this is the U, depending on your favorite way of thinking about it. And if you just work out so this spacing is very small. It's 1 over n, and this is precisely the 1 over n that Igor mentioned when he went from the non-singlet to the non-singlet sector. There was a small gap of 1 over n, not exponentially small, but 1 over n. But as n goes to infinity, that also shrinks, and the charge is a continuous function. And if you take this derivative of how q changes the mu, you'll find that's the compressibility. Or how the energy changes with charge. The energy is 1/2 cv squared or q squared over 2c. This is exactly those formula here. And you can get the compressibility by the second derivative of the energy. Okay. So that bit is freshman physics. Well, okay, first year graduate physics. Okay, what's the rest? Well, the rest involves f of tau. So there's two pieces to it. One is this here. There's an additional term called the Schwarzian, and that turns out to be, where's, I've written it down somewhere. I want the coefficient. Yeah, so it's minus n. Okay, I'm putting n's over there, so let me remove the n over here. N gamma over 4 pi squared, 0 to 1 over temperature, d tau tan f of tau. And what is this squiggly symbol? The squiggly symbol is g of tau, is g triple prime, g prime minus 3/2, g double prime, g prime squared. Okay, that looks like a completely horrible function. How did anybody ever think of it? Well, it has a very special property that if I take g equals to a tau plus b, c tau plus d, then squiggle g of tau is 0. So this means that if my reparameterization f is SL2R, then the action is 0. Well, that's great, because if you do an SL2R transformation, it maps sigma s back onto itself, so nothing changes. So that's how this was. Well, Maldacena and Stanford's paper where I first saw it, although they do give credit to Kitaev for having proposed it first. I don't know. Okay, anyway. So this is the finite temperature generalization of it. Is there a pi missing somewhere? Yeah, there's a pi t here. Oops. Anyway, the notes are, well, I don't know if they're online yet, but if they're not, they're on my website. Just Google my name and you can see them. Okay. So, and what about this coefficient? And why did I put this awful factor of 4 pi squared here? Well, you can do the path integral over the, or in fact, you can just evaluate the Schwarzian for f of tau equals tau, which is the saddle point that one wants with no reparameterization. Then this thing becomes basically minus n gamma t squared over 2. That's what it evaluates to. And this, what this means then, since this is just precisely the grand potential, it tells you that the entropy S of t is S0 minus gamma t. So it's the same, plus. It's the same gamma I introduced for the SYK model for the black hole, and that's the coefficient of the Schwarzian. It determines the linear dependence of specific heat at the saddle point level. So this was, in fact, we did, to give credit where it's due, in the 90s, we actually did worry about what is the specific heat of the SYK model, or the version of it that we were studying. And we were kind of flummoxed by it. We didn't know how to make it work. But now this is the answer. It goes linear into even at the large n limit. It's a complex.
Gamma is only known numerically.
Right. So is K. So K and gamma are, these are thermodynamic quantities.
Right, but in some sense that means you haven't really derived them from the SYK model. You guess them up to this coefficient and then you try to match them.
Well,
To say that's the stage we are.
no, I mean, there is some complicated integral equation you have to solve, and you can solve the integral equation numerically. I mean, you start from this is not an exact diagonalization study. You can just start literally from this path integral, and you have to sum this ladder diagrams. Normally, the way you sum the ladder diagrams is taking the low energy approximation of the Green's function. You don't do that. You solve the integral equation numerically for the exact Green's function. It's just a numerical integral equation, and you can get the values of K and gamma. No, for any Q,
Large Q,
numerically.
For large Q, you can do it analytically.
Yes, yes.
But for Q equals 4.
Well, for K, we're just finishing a paper getting the value of K. There's some subtleties. Anyway, all right. Anybody else except these two? Where? Oh, yes. What is this? So this turns out to be, that's of course my pet thing. So there's a little shift here. So notice what this is related to the fact that I told you this action here was just a rotor representing a capacitive energy for the SYK model as you add more charges. And you notice that adding charge 1 or adding charge minus 1 had the same energy. And the amplitude, everything was the same, particle symmetry. But in general, it's not. So you're not too surprised to discover that there's a shift here, which is like a chemical potential. And this just turns out to 2 pi. Again, the famous 2 pi E. And there's an I here. There's a temperature. And there's an F prime of tau. Okay. So there's a little kind of particle hole asymmetry that comes into the capacitive energy. It's the density of states to add a charge and remove a charge is not exactly the same. All right. So now, how much time do I have? I have 10 minutes, right? Yeah. Any other questions? The number, I don't remember it. So it depends on, SYK4 is something. For the black hole, it's something else. It's just some number that you can evaluate. So one important property is, unlike S naught, so S naught for the SYK model is completely universal. That is, it only depends on Q and nothing else. Gamma and K depend on everything. They depend on all the UV details. There's different values for different systems. But what's always the case is that, as I said, ds dq is this E over here, and so on. So what I claim is, and this has been shown at various levels by different people, probably somebody needs to write one comprehensive paper showing all the steps, including there's a very nice paper by Sandeep Trivedi's group at TIFR and the people here in the audience who worked on it, who kind of gave further evidence for the existence of this term here, and there's many papers deriving the Schwarzian. Okay. Yes.
So I should have asked it earlier, probably, but when you average over the disorder, the SYK model was expecting some replica in it or something similar?
Yeah.
Or how
Right. So I've skipped all those steps. I'm only just looking at the replica diagonal solution, and the replica diagonal solution, it doesn't make any difference whether you do it or not. So now you can ask, so we found the replica diagonal solution. Now, now Sherrington Kirkpatrick found the replica diagonal solution, and it was not right. And Parisi discovered you had to break replica. Oh, there was a replica off diagonal solution, but then you have to further break replica symmetry. So for this model, it turns out, at least in the larger limit, you can show that replica symmetry is not broken, and there are no replica off diagonal solutions. And the reason is actually crucially connected to the fact that they're fermions. You give a replica index to a fermion. If you have replica off diagonal solution, it means you're condensing a fermion, which you can't. So those solutions just don't appear. Now there's some estimates for this model that the critical temperature for replica off diagonal effects to appear will be e to the minus n. But that's totally meaningless because that time you have to worry about discrete energy levels. So I think that has been thoroughly examined and thoroughly settled. Yeah.
Some jump that I couldn't follow.
Yes, please.
The integral of the thermonic fields with the SYK and so on.
Yes.
How did it come to be an integral of the G and sigma, which are
Okay, I will show you. Want to see that? Okay. Well, let me just schematically indicate how it works. So you have Z is df, the fermion fields e to the minus f, and then you average, so there's a j here, so you do an average, so then you get e to the minus f, well, whatever, squared, and then you decouple this, so then you do the integral over f. No, sorry. You decouple this, so you write this as d g times e to the minus f g inverse f plus g to the power 4 or something like that. I don't know. Then you do the integral over f, and you have a sigma somewhere else. And these are two Hubbard-Stanovich fields, which plus there's a sigma g or something like this. Yeah, all right. Anyway, so this is exact. This is just a Hubbard-Stanovich transformation. Then you interchange the order of integration. You integrate over f, and you get dt sigma. Okay, it's a very standard thing, which is easy. Amazingly, it's easier for the disordered model, and this is the kind of thing that's very, very hard for the tensor model, as Igor was showing.
No, it can't work. It can't work. I think it's because if you've got it.
Okay, all right. There's maybe more fields, right? Fair enough. Yes. Yeah. No, that's okay. But there's some evidence that these Schwarzian modes are there, even there. Okay. All right. Okay. Now that we have this action, what does it imply? Okay. I have less than 10 minutes left. I'll continue maybe on my in my next lecture a bit more. So what you can then compute are the 1 over n corrections to the free energy and other quantities. But rather remarkably, it turns out that some expressions can be computed to all orders in n, including e to the minus n corrections. This particular partition function of the Schwarzian of this horrible set of nonlinear functionals can be done exactly. There was a beautiful paper by Witten and Stanford showing that. This integral is trivial to do exactly also. It's just a Gaussian integral. So I won't focus so much on the charge part, although that's what I've been working on, and just recall some of the results that come from doing this path integral. All right. Okay, so let's express in terms of the entropy. So the entropy we found was some S naught. So actually, I should also mention this S naught doesn't appear anywhere. It's just an overall constant out front. You have to compute that from the way we did it. It has nothing to say about S naught. What it does have to say something about, let me put an n here, make the n dependence explicit, gamma t. And then you can ask, what are the corrections? Well, there's some strange powers of T that appear here. I won't say more about them. But they turn out to be the contribution. The Schwarzian gives you this gamma T, as I just showed you at the saddle point level, gives you this term here. That's what fixes gamma to be this coefficient here. But you can do a path integral. And the remarkable property is the Schwarzian has this property that the Gaussian is Gaussian exact. If you just do the Gaussian approximation, you get the exact answer. Why that is, ask Douglas. Is there some strange, beautiful lemma of this space that you're integrating over, which is diff S1 mod SL2R. Okay, so if it's Gaussian exact, well, then it's an integral even I can do. And then you get a correction here, which is of order 1, and it turns out to be, and I don't remember the sign, it's either plus or minus. I think maybe it's minus 3/2. What is it? Log T. Yeah. Okay, again, I'll refer you to the notes to look it up if I don't want, I'm running out of time. So this is the 1/n correction. And the point is, from the Schwarzian, there's nothing else. This is it. There's nothing else at all. No corrections to order 1/n in the Schwarzian approximation. And this is for the Majorana case. For the complex case, it's 2. All right. So, yeah. So now we notice here that as t goes to 0, this term will eventually become more important than this term. And that's when the theory will break down. So when does that happen? Well, you can see that happens when t is of order e to the minus s naught. There's a t over j here. Minus n. So the theory is in excellent shape until the temperature is exponentially small. Now, what is this energy scale? This energy scale is precisely the spacing, many body level spacing, very, very tiny. So if you're really worried about the discreteness of the energy levels, then the theory breaks down. You have to actually worry about replicas and disorder and everything else. But if you're not, you're kind of averaging over this very tiny scale, it's perfectly good. Okay. Now, one of the things people have been computing from this, and actually from the grand potential, or you can take the grand omega over t, we know this now. We know the entropy, for example. We can write this as an ordinary integral, 0 to infinity, E0 to infinity, dE d of E times e to the minus e over t. So if you know omega is a function of t for all t exactly, in principle you can use this representation to determine d of E. So d of E is what people call the density of states, but let me emphasize that by saying it's the many body density of states. Okay. And another thing to remember is that you may be feeling very good that you've got a 1/n expansion for omega, and therefore you say, I'm going to plug it in here and get a 1/n expansion for d of E. That doesn't work that way, because you have to do an inverse Laplace transform to get d of E. It's an ill-posed problem. Just because you have a good expansion for d of s of t, it doesn't mean that you're going to get d of E, at least at all possible energies. The inversion is not commute with 1/n expansion. So it might seem like there's a pointless thing to do, but because this is an exact expression, at least in this Schwarzian theory, you can determine d of E exactly. Okay, but before I tell you what it is, what I want to do is tell you what it is for the ordinary random matrix problem, where in fact some part of it is easier to do, other parts even harder to compute. It's not a thing that you want to compute in condensed matter physics, but if you're applying to nuclear physics is something people are very much interested in, this d of E. Anyway, but I'm out of time, right? So I will continue. Huh?
Right on time.
Okay, I will talk about this d of E first for the free fermion problem, where it's related to the number of partitions of an integer, and then tell you what we know it is for the Schwarzian theory. And I'm sure Douglas will say more about it too. All right. Thank you.